This video, we're going to start looking at Faraday's law and stoichiometry. So this is cell stoichiometry. And essentially, because we get a reaction that has a number of moles reacting and producing a number of moles of product, we've got a relationship, a molar relationship between the number of moles and the chemical amount. So for instance, if we had sort of copper 2 plus 2 electrons makes copper solid, I get 2 moles of electrons make 1 mole of copper. And if we understand that relationship and know how to do our basic stoich using stoichiometric ratios, we're going to be able to use that to be able to calculate the amount of product being created. Before we can get to that, though, we need to take a look at Faraday's law. And Faraday's law connects the number of moles of electrons to the amount of charge. And so Faraday's law allows us to find the mass of metals electroplated in the cathode or oxidized at the anode. So we can find the mass of metal electroplated or lost. We can know the flow of electrons or the amount of current, and our current is measured in amps. So to do that, we're going to need to involve some time, and for this purpose, all our time is going to be used in seconds. So we're going to need to also know the relationship of seconds to minutes to hours to days. So if I have 1 minute is obviously 60 seconds, 1 hour is 60 minutes, so it's going to be 3,600 seconds. So that's 60 minutes times 60 seconds per minute. And then if you wanted to find the number of seconds in a day, you'd need to multiply that by 24 hours. So 3,600 times 24, so we'd get like 1 day is equal to 86,400 seconds. In no way are you supposed to memorize that. You should be able to figure out what the number of seconds is. Now, mathematically, there's a relationship between the amount of current and the charge, or the quantity of electrons that travel. And that relationship is here, where Q is the quantity or the charge in coulombs is equal to current times time. So if you look in your data booklet, it shows this relationship, but it's kind of subtle. So you don't actually get an equation, but if you look at current, so current's symbol is I, times second is T, in seconds. And we also have Q is the charge, right? So charge is in coulombs. But if I look and I recognize that, so A is current, current equals the charge over the time. And if I rearrange that, Q equals IT. And that's our formula that we have in here. So this formula you're not given, but if you recognize in the data booklet that this relationship where the amps is equal to coulombs per second, and then you just give the symbols. So current is I, Q is charge, and T is time in seconds, and then solve for Q, you can actually find that equation hidden in your data booklet. So this formula can be used to find the relationship between time and current and coulombs, but it becomes interesting when we start to relate that to the number of moles. So example one question in example one is using this formula. So we'll just deal with that one quickly here. So it says, oh, sorry, no, this is related to this formula. So the formula here has the number of moles equals current times time divided by Faraday's constant. Now, Faraday's constant is also provided in the data booklet, and it's in the list of miscellaneous values. So Faraday's constant is 9.65 times 10 to the 4 coulombs per mole of electrons. And so if we go back to this question, the number of moles of electrons equals current times time over Faraday's constant, because current times time is equal to Q over F. And so we're going to use this formula to calculate this. They want to know the chemical amount of electrons. The current is 1.74 amps, and the time is going to be 30 minutes. So it's going to be 30 minutes times 60 seconds per minute divided by, and I need to put all of that in brackets, divided by 9.65 times 10 to the 4 coulombs per mole of electrons. So when you're putting this into your calculator, you really want to make sure that you have your order of operations correct, because you need to have this whole thing is what you're dividing it by. So I'm going to take my 1.74 times 30 minutes times 60 seconds per minute, and then I'm going to divide it by coulombs constant here, and what I end up getting is 0.0325 mole of electrons are transferred. And so the number of moles of electrons transferred by 1.74 amps in 30 minutes is this value. We're going to take this another step further and apply it to a half reaction. So in this question, we're going to need to repeat this kind of calculation to find the number of moles, and then we're going to apply it to copper being refined in an electrolytic cell. So now we're going to do cell stoichiometry. For cell stoichiometry, you need to have the half reaction. It's much easier to do with a half reaction than it is to do with a complete reaction, because we get 2 moles of electrons makes 1 mole of copper. Now we want to know the mass of copper, right? It says, what is the mass of copper? Well, the molar mass of copper is 63.55 gram per mole. And I know that the time here is 40.0 minutes. So I'm going to multiply that by 60 seconds per minute. So 40 times 60 is 2,400 seconds. And the current is 12.0 amps. So you can see that this is a pretty big current. And so what I have now is I've got enough information to get the number of moles of electrons. So the number of moles of electrons is current times time over Faraday's constant. So it's going to be 2,400 seconds times 12.0 amps divided by 9.65 times 10 to the 4 coulombs, times 10 to the 4 coulombs per mole of electrons. And so I'm going to put that into my calculator, and I come out with 0.298 mole of electrons. But I want to know the number of moles of copper. And so I take that number of moles of electrons, 0.298 mole of electrons, and I get 2 electrons for every 1 copper. So I'm using the coefficients here to find the number of moles of copper that are going to be produced. And so I get 0.149 mole of copper. And so then I can get the mass of copper, and I'll take 0.149 mole times 63.55 grams per 1 mole. So I get 9.48 grams of copper are going to be plated in this cell. So the 12 amps for 40 minutes plates 9.48 grams of copper. And this is essentially how cell stoichiometry is going to work for all questions. So I'll put a break in the video and we'll get a chance to look at another kind of question. But essentially, all redox stoichiometry is going to be based on half reaction, number of moles of electrons, and a mass of a product or a mass of a reactant used.